In this video, I'll be explaining the first topic of the interpolation series, namely Newton interpolation. So recall that this is a form of polynomial interpolation. I'll first be discussing first-order Newton interpolation, thus the linear interpolation. Then I'll be moving on to a general form, and finally I'll be discussing an example as well. So the problem in linear interpolation is to find the straight line, thus the first-order polynomial f1 of x, that passes through the two data points that are given. We can set them as x0, f of x0, and x1, f of x1. So this situation is depicted in this figure here. We'll have two data points, the two black dots, and we're going to draw a straight line, f1 of x, through the two data points that will approximate this function f of x that is given in black. This is not a very difficult task to do. We can use a graphical method. For example, we'll use similar triangles to find f1 of x minus f of x0 over x minus x0. So this is the ratio of the sides of the smaller triangle that is drawn in the figure. That is going to be equal to the ratios of the sides of the larger triangle. And then you can rewrite this expression to find this equation. This is the final expression for the first order polynomial f1 of x. And therefore this is just the general expression for the linear interpolation. So you can kind of guess that if you increase the distance between the two data points, your approximation is going to be less accurate. You can see that in this figure as well. We'll have this function f of x is the natural logarithm of x. And we have two estimates for the polynomial f1 of x, and they differ in the distance between the two data points that are used. And you can see that as the interval between the data points becomes smaller, your polynomial is going to be closer to the actual function, and therefore your interpolating variable, or your interpolating value is going to be closer to the true value. So now we can write a general form for the Newton polynomial. So the nth order Newton polynomial, fn of x, is going to be given by this summation, where the b's are coefficients, and they are given by the following expressions. So b0 is f of x0, and b1 is the finite divided difference between f of x1 and f of x0. And you can continue this process up until bn. So these coefficients b are finite divided differences, and they are calculated recursively. So this means that for the second finite divided difference, you use the expressions for the first finite divided difference. They can be calculated with these formulas. So this is just the general expression for any first finite divided difference. So this is given by f of xi minus f of xj over xi minus xj. And then you use the first divided difference to calculate the second one. And in such a way you can continue until you obtain this expression for the nth finite divided difference. So this recursive nature is presented here in this table as well. So you can see the values of the independent variable x and the dependent variable f of x are given in the second and third column, and then you calculate the finite divided difference in each step using the last ones. So lower order differences are used to calculate higher order differences. And this recursive nature makes it very efficient to compute and makes it so useful to use in computer programs. So now we'll be discussing an example. So let us have these values for the thermal conductivity for the element mercury. So we are given the thermal conductivity K for 4 different values of the temperature T. And now the question is, what is the thermal conductivity at T is 600 Kelvin, so at a point somewhere on this interval. And we're going to use Newton interpolation to estimate this. So we have these 4 data points. For T is 300, 400, 500, and 700. And therefore, we're going to have 4 coefficients of B naught. And we can calculate it. Okay, wait, let me put N is 4. So we're going to find a third order Newton polynomial. So we have to calculate the coefficients for this. So B naught, recall, is the value of the dependent variable at the first data point. So this is going to be K naught, which is equal to 0.084. And then we continue to the first finite divided difference. This is going to be the divided difference between K1 and K naught, which can be calculated with this expression, K1 minus K naught over T1 minus T naught. So this is going to be equal to K at 400 Kelvin minus this K at 300 Kelvin over 400 minus 300. Yep, 14 over 100 is going to be 0.00012. One four actually. I don't know why I have that in my head. 1, 4. So, to calculate B2, we have this expression. We use the finite divided differences of K2 and K1 and K1 and K naught, and divide it by this. So we already have this value. This is going to be this finite divided difference. So now we still need to calculate this one. So K2 and K1, the finite divided difference is going to be given by this expression. And again, we can plug in the values for K2 and K1. So K2 is the thermal conductivity at 500 Kelvin, and this is again 0.098 divided by 500 over 400. This is going to be 0.011 over 100, and then we have this. Now we can plug this in to this expression for B2. So this is going to be this. And finally we can calculate this coefficient B2 by just yeah, 0.014 divided by 500 minus 300. So this is going to be lots of zeros over 200. So we actually have let me just write it still with zeros. Zero, 0.015. Okay. We can continue this process to obtain all the coefficients. But obviously, usually you will not do this by hand, and you can just use a function. So this is the function that I used or created in MATLAB to calculate the finite divided differences. Yes, so you can create a table with this. So as you can see, we calculated the first finite divided differences in column 3. So it is 1.4 times 10 to the minus 4 and 1.1 times 10 to the minus 4. And we use those two to calculate the second divided difference of minus 1.5 10 to the minus 7. So as you can see, the coefficients of B0 until B3 or until B4 are going to be the first column of this table. We can plug those in to the expression for the Newton polynomial, and then we obtain this equation. And we can plot that in MATLAB as well to get this polynomial, third order polynomial, through these 4 data points. And finally, we obtain our solution, where we can use this polynomial to estimate the value of the thermal conductivity K at 600 Kelvin.